Okay, hello everyone. I just spilled all my water, so pretty weird how this started, but whatever. So I'm Carlos. I work at the Ethereum Foundation, and today I'm gonna showcase one of the projects that we've been working on for like 5 or 6 months, probably, which we haven't revealed anything about so far, which is called BloatNet. So BloatNet basically tries to answer a lot of the questions that from the protocol team we have. Basically, what happens when Ethereum stake gets to terabytes? What happens if a contract storage reaches 20, 30, 50 gigabytes? What if we start getting like extremely deep tree branches on the Merkle-Patricia tree that affect read-write time? We want to go to 300 million gas, 1 giga gas, 1 tera gas, and all of these things. But we actually need to make sure that the network is resilient and can actually withhold this load. So what we basically did is we took mainnet and we made a shadow fork of it. For those who don't know, shadow fork is basically we just cloned mainnet and we just gave it a different network ID. So basically we can replay all mainnet transactions in BloatNet, but at the same time we can issue anything that we want in BloatNet and bloat it further, make it bigger, do whatever we want, deploy all our setups, etc. So basically we have, it says 4, but it's 5 clients. We have all of them except from Etherex and Nimbus. And basically, what we have been doing is creating all of the machinery such that then all of the teams and basically any independent researcher can actually come and test and explore anything they want. So basically, just to make a quick explanation, we have collaborated with ETHPandaOps in Spamor, which is basically a tool that allows you to mass transact at gigagas per second levels, so to generate an insane amount of transactions and bloat an entire network and mempool and process as much gas per second as you possibly can. We have Benchmarker, which is a tool made by Rafael, also from the ETHPandaOps team, which has been extremely helpful at looking at all the data and analyzing all the benchmarks. The execution spec tests by the Steel team, where we have integrated or continued the work from Ignacio and Kev from the CKVM team, including a lot of benchmarks for state-related operations. And then with Gary from the Geth team, we coded these slow block metrics, which are actually, up until this time, we didn't have any way to compare performance between clients, like there were no standard metrics and we couldn't see inside of their block processing timeline, like how things were performing. Now we finally can. Special mention also to Syncor, which is allowing us to also test syncing time and performance for all of the different clients. So this that I have here is basically for you to see. This is Benchmarker. It's a lot more extensive than that, but this is just a simple way to see it. And the most important thing is it gives us a heat map of how are we performing in terms of megagas per second so that we actually know what the network can handle or not. So if we are actually targeting 100 million gas block limit, that means with 4 seconds of execution, and that is being extremely generous, we should be at 25 million gas per second, right? This is Geth. It's arguably one of the most performant ones in state-related operations. And as you can see, we definitely have 57 out of 649 tests, which are actually performing a lot worse than 25 million gas per second. So we're not even at the 100 million mark yet. The good thing is this allows us what we basically need to optimize or start looking in order to make it better. And that's what we did. So the results basically showcase 2 big areas. One is contract storage size. So the bigger the storage of a contract gets, the worse the performance becomes for reads and writes. Like this sounds obvious, right? I mean, sure, it's bigger, so the performance is definitely worse. But the interesting stuff is not all clients have the same database types. Not all clients interact with the state on the same way, and we might be pricing state differently to what actually, how much effort does it take clients to actually fetch storage. So for instance, you can see here the performance of S-Load and S-Store in a wide range of different contract sizes. And as you can see, most of the clients basically tank on throughput when contracts get up to 10 gigabytes or 30 gigabytes. And for reference, 10 gigabytes it exists on mainnet. Like that's Zen. I don't know if you know that contract, but Zen is like more than 10 gigabytes. And it's in mainnet living now. Like people can actually transact with it. So this is definitely something that we need to optimize for if we want to bump up gas limit up significantly. Same happens with S-Store, and this is definitely not a surprise. Maybe for Reth, I was definitely expecting something not as bad, but I'm pretty sure this is fixable. I mean, that's just optimizing things that they probably haven't thought about yet, because no one does these types of blocks. But the TLDR is storage. S-Store basically needs reads prior, so that we know if we are actually going from 0 to non-zero or from non-zero to 0, because we price differently these operations. So since we need to do a read, we at least know that this is going to perform as bad as the read, if not worse. And it becomes worse, because the state root recomputation forces you to fetch a lot of extra data. So what we can see is we have a range from 9 to 64x of degradation when the contract sizes go bigger. And probably you know it, but contract sizes are unbounded. Like we can transact as much as we want, and we can make them grow as much as we want. So from the protocol perspective, there's no solution in place at the moment. Like this will grow forever. And if you take USDC, and we assume that half of the world will use it at some point, and if we go AI, it's probably even crazier, we're going to have billions and billions of leaves under this tree. And this will get bigger and bigger and bigger, and probably out of control at some point. So we did another thing, another cool experiment, which is, okay, let's just make bloatnet twice the state size. And remember, state is not history. So state means all the accounts, all the contract storage, and all the bytecode. No blocks, no receipts, no logs, nothing like that. Like you can just drop all of this. And so when we go twice mainnet size, but keeping the same ratio, which is 70% contract storage, 20% accounts, and 10% bytecode, we actually see that the difference between mainnet and bloatnet in performance for the same benchmarks is actually not that different. The only client that actually shows that is Nethermind. And at the beginning, I was definitely impressed. Like, if you see the performance heat map, I mean, in some of them, notice we only have one run at the moment, so I mean, there could be variants. But some of the scenarios are actually better in bloatnet than they are in mainnet. And bloatnet has almost 700 gigabytes of state, which is twice as what mainnet has today. So the question begs itself, which is, how is it possible that twice the state is not twice slower in order to process everything, right? And so the explanation is fairly simple, but if you understand the protocol, the thing is, Ethereum is read dominated, basically, and it makes sense. If we want to execute, we need data to execute over, right? So we need to read it from somewhere. So reading is mostly all of the operations. When you count writing, well, when you write, you need to read first, even if you don't want it, because we need to compute the gas of the transaction, and you need to know what was the previous value in order to price it correctly. So every write is a read, every read is, of course, a read. And when you recompute the state root, you need to also read a bunch more nodes in order to get all the siblings and get to the root. So this is one thing. We're read dominated, and read is definitely not nice in an MPT or basically in any kind of hashed table, in the sense that if we cannot directly look up, everything is random. Like everything is random reads, and random reads are unpredictable. So there's no optimization that we can like magically pull off. The other one is, one of the things that explains the performance is not twice as bad is basically the MPT and any sort of tree has a logarithmic cost with respect of the size that it has, right? So the amount of levels that I need to traverse the tree downwards is logarithmically proportional to the total amount of data that I have stored in the tree. So the MPT is a hexary tree, so it means the logarithm is base 16. So going from probably the average tree depth, I think in Ethereum right now is between 6 and 7 in the account try. To go one more level, we need 16 to the 7 or 16 to the 8, depending on where we are. And if you compute that, that's indeed a very huge number. And it turns out that if you double the database size, you are actually not going over this number yet. I mean, you could triple it. You can go to 2 terabytes, and you will still be in the same place. So this gives good news in the sense we might not be that bad increasing the state size if we don't massively increase one contract or if we don't focus in a particular place, making a subtree extremely huge. So that's good news for all of us. The bad news is, well, the disks that we all own are probably commercial hardware, right? Which means the best NVMe or SSD that you can actually get is 4 to 8 terabytes. And getting something that is bigger than that is actually quite hard in the times we live in, but on top of that, it's extremely expensive. So it might not even compensate you as a staker to actually have that, right? So some other benchmarks that we have run and have interesting insights. There's a lot of people that want like bigger bytecode size. I actually made all of the benchmarks and actually pushed in ACD to get to 64, but only 32 was accepted because ACD reasons. So what we see is most of the clients actually are okay, basically fetching bigger and bigger and bigger sizes. I think that their score comes at 128. If we look at powers of 2 there, we might need to do some optimizations. But as of now, fixing some issues or some like database page related stuff in Geth, we should be definitely fine. So not much to be worried about there with respect to the bytecode impact. Then we go to the mixed S-load and S-store benchmark. So here, basically, what I do is I have a block, and it's targeting an ERC20 that I minted and I bloated. And what I do is I make transactions to it with S-store and S-load to completely random slots. So they are all empty and out of the cache. And I see I vary the distribution between reads and writes, right? So what we see is the more we read, and here is very obvious, the more we read, the less throughput we have. And the more we write, the better we are at throughput. And this has a very simple explanation. Even if we are logarithmic in reading, reading has a cost of 2,100, I think it is, gas. So that's what S-load costs. And writing, which is S-store, has a price between, I think it's 4,800, so double, if the slot already has a value. And if it's 0, you will pay 20,000 or more. So definitely, you can do a lot less writes than you can do reads in a block. That definitely explains why the more reads you have, the worse it becomes, because the load is the same when reading and writing, but on top of that, you can do a lot more read than you can do write. So that already hints us that there might be something that we might need to either reprice or consider. The thing is, it's tricky, because if you price reading heavily, then what am I supposed to do as a user? Like, the only thing I can do is read and operate with the data I read, right? So if you price me reading heavily, then you are limiting basically all of the operations or all of the use cases that I might have. So it's definitely an interesting question to actually check. Let's go to worst cases, which is the spicy part. You need to take into account that these benchmarks have been, for the first time, taken by us probably like 1 or 2 weeks ago. So there's a lot of benchmarks that need to be refined. There's a lot of things that we need to rework. And client teams especially have had no time yet, because they probably don't even know some of the data to basically optimize any of these things. But if you count the 2-second mark, so if you have Geth running and you are a solo builder, which I'm not sure if there's any here, but there's me, maybe. Geth, when you arrive at the 2-second mark, will emit an empty block so that you don't miss the spot, basically. You don't miss the slot. You propose at least something, right? As you can see, we have plenty of mainnet and bloatnet benchmarks that I was able to craft, where my Geth node, or my Reth node, or my whatever it is, would have basically not been able to produce a block in time, and the block would have been like half empty, like even more empty than they are, because the mempool is a bit poor nowadays. If we go over the 4-second critical mark, which is basically if you don't ship a block at this point, you basically missed the entire slot. You see that there's still plenty of benchmarks, especially in bloatnet, which is the orange one, where if we get to 100 million gas and we get to 600 gigabytes of state, we are in this like dangerous territory, let's say. And this is just showcasing the top 20 slowest cases on bloatnet and mainnet. You see that the scale arrives to even 70 seconds of re-execution. Like you are probably re-executing now the average block in, I mean, a second will be even a lot. So 70x times that is insane. Of course, these are not the classical blocks that you will see in mainnet. That is definitely done on purpose to exploit as much as possible the clients. But that is already hinting us something, which is if we want to be able to scale the network up, we need to rework the state somehow. We need to reprice it. We need to make it faster. We need to work on clients, optimizing things. We need to figure out how to scale state up, because otherwise we will arrive to some of these blocks, and one block is okay, 2 blocks is okay, but if we have 100 blocks that are consecutively this thing, either we don't send any block to the network, or half of the network basically is not keeping up with the chain because they cannot re-execute, right? So this is not to get alarmed. The contracts that I deployed don't even exist on mainnet. They are specifically designed to abuse reading and storing data. On top of that, notice that a lot of these contracts have like 50 gigabytes. It would cost you like hundreds of millions of dollars to bloat 50 gigabytes in a single contract, right? So this is not realistic now. But what this is trying to anticipate is in 10 years' time, we want to know which will be the issues that we can be facing or that we will be facing, such that we actually have the chance to start working on solutions now. Because optimizing the client code, I mean, it's definitely complex, but it's doable. But when research comes into play and you need research in order to solve the problem, research is something that might not yield anything for like 5, 6, 7 years. So we need to start now, and otherwise we'll be a bit cooked. The key takeaways for people out of this presentation is, I would say, don't get alarmed. This is not to alarm people, but this is just a wake-up call for us to make sure that we understand the consequences that scaling up will bring, and they are obvious. We've seen them. So if we all as a network, as an ecosystem, we think that we need all this throughput, then we definitely need to put a lot of resources and work into actually making it viable and secure. Like otherwise, yeah, we have the chain and someday it magically breaks and all of us are basically in deep trouble, right? Besides that, it's also important to realize that deep writes are especially one of the most dangerous areas that I see, in my opinion. Like creating deep branches on the MPT is not especially costful, I would say. It's true that in order to maintain such kind of attack, the cost will be unbearable. But definitely for some blocks, like you can force the network to do that for some millions, right? This will not be an issue for Ethereum. Like the chain will just continue and that's it, and that person will have lost millions. Sure, pretty useless. But it reveals a pattern, which is if on average the depth of our account tree and our storage tree gets deeper and deeper and deeper and deeper, then we might be in trouble in front of some transactions. Bytecode size increases below 128 kilobytes will definitely require a lot of careful evaluation. Like it's not trivial at all once we go past 64, that we can do that just by changing to constants in the database of the client, sorry, in the code of the client. Finally, I want to say that we at least from the protocol, we want to transmit that block access lists will definitely dramatically improve this, at least for all of the validators, which is most of the people that are here, mainly because you have and you receive all of the new values for all of your leaves at the beginning of the block. So you don't basically go blind fetching every single thing. You already have that from the beginning of the execution, and that allows for huge optimization landscapes, parallel transaction execution. There's a lot of improvements that will come that haven't been benchmarked here yet, but this benchmark where we were pre-Fusaka, basically. And pre-Fusaka, if we would have gone to 300 million gas, we would be in trouble. So bear with us, keep posted. Thank you very much to all the team in the EF that has worked on that, because I'm just here giving the presentation, but there's been work by a lot of the teams. And happy to answer any questions about that. Hopefully you can use all this tooling that we've created in order to benchmark your own machines or do your own research. And we are happy to be in touch with anyone that has any insights. We would be extremely happy to collaborate, listen, and just learn from your own experience in your machines. So yeah, thank you very much.
We don't really have time for questions. Sorry.